So let's consider the first factor, position of ion in the activity series. You see, when two competing ions migrate to the electrode, either the cathode or the anode, the ion that is lower in the activity series between these two competing ions is the ion that tends to be discharged. Let's say, for instance, now, copper and hydrogen migrates to the cathode. Well, because copper is lower in the activity series, then copper will tend to be discharged if other factors are not considered. Now, one thing to take note here is that this is the activity series for cations and the activity series for anions. So whenever two ions migrate to any of the electrode, you check the one that is lower, then that ion should be discharged if other factors are ignored, are not taken into consideration. Now, another thing I want to say here is that some call this the electrochemical series. Well, there's a remarkable difference between electrochemical series and the activity series. And that's the fact that electrochemical series simply shows you the potential of the ions. So if I write potassium, I should write the volt, minus so and so volt, sodium so and so volt, and all that. That's number one. Number two is that the electrochemical series, that in the electrochemical series, calcium comes before sodium. So any series where you have sodium coming before calcium, as it is here, is the activity series. But if calcium should come above sodium, then that should be the electrochemical series. So don't confuse them actually. So the right word here to use is activity series, not really electrochemical series. In some authors still call the electrochemical series and clean up the calcium from these ions here, whichever way, but take note of the difference. So that's that about this. Now let's take some examples on electrolysis. So the first compound we are considering is dilute sodium chloride. So let's see the electrolysis of dilute sodium chloride. Well, the compound is sodium chloride. Dilute means it contains water. Henceforth, the sodium ionizes into sodium ion and chloride ion, and the water ionizes partially into hydrogen ion and hydroxide ion. Now, all the positive ions will migrate to the cathode, and all the negative ions now will migrate to the anode. Now, if sodium and hydrogen migrates to the cathode, obviously, if you look at the series I gave to you earlier, you see that hydrogen is far below sodium in the activity series, so hydrogen will be discharged. So this is it here now. Both sodium ion and hydrogen ion migrates to the cathode, but hydrogen ion is discharged because it is lower in the activity series. So what happens when hydrogen gets to the cathode? It accepts electron and becomes discharged as hydrogen. But you see, hydrogen is not discharged as elemental, it's discharged as a gas. So we need another hydrogen again to accept another electron. That is now two hydrogen accepting two electrons and being discharged as a gas. And this is what happens at the cathode. Now, at the anode, what happens? Both chlorine and OH migrates to the anode. But by effect of position, you see that OH is the ion that is lower in the activity series. So OH is discharged. Now how is OH discharged? You see, OH give out its electrons and becomes like this. But OH is not a compound. It actually changes to water and oxygen. And how does that happen? We need about 4 of OH to be discharged as this 4 OH plus 4 electron, meaning that 1 OH gives out 1 electron, so 4 OH should give out 4 electron. But this OH, 4 OH now will not split into 2 molecules of water and then plus oxygen gas. And that's what actually happens. So whenever OH is discharged, this is the equation we use. Change the 2 molecules of water plus oxygen gas. So that's what happens at the anode. So let me illustrate this with the simple electrolytic cell we've drawn before. You know, if this is the electrode, okay, and so this is sodium chloride here, dilutes. Now this is the cathode and this is the anode. And so the ions here, the sodium and hydrogen here comes here. Sodium ion and hydrogen comes here. While this part, the chloride and OH comes here. And so take note that one of these is discharged, like we said earlier. So hydrogen is discharged here because it's lower. So on this electrode, which is the cathode, you see hydrogen gas leaving off. While on this part, which is the anode, you see OH leaving in form of water and oxygen gas. So that's what actually happens. Although our electrolysis does not actually look like this. This is just for illustrative purpose, but that's just what we have. I will not be drawing this actually. Just want to illustrate to go along with what we just said here about electrolysis of dilute sodium chloride. The example here is electrolysis of acidified water. You see, acidified water is actually just dilute H2SO4. And the electrolytic cell used for this electrolysis of acidified water is known as Hoffman voltameter. So this is the Hoffman voltameter. Now, mind you that, like I said, the electrolytic cell we use for electrolysis doesn't actually look like the simple electrolysis cell I often draw. And so this is just how the Hoffman voltameter is. So if you go to the laboratory where they sell laboratory equipment and you decide to buy the electrolysis cell used for electrolysis of acidified water, you just need to say, I want to buy Hoffman voltameter. And they give you this. And whenever you're buying that, they know that you want to carry out electrolysis of acidified water. But that's been said now. Like I said earlier, acidified water means dilute H2SO4, tetraoxovacic acid. So you see, the electrolyte is the H2SO4 and it ionizes as shown. The H2SO4 ionizes to hydrogen ion and SO4 2-. And water ionizes partially into hydrogen ion and hydroxide ion. Now all the positive ions move to the cathode and all the negative ions move to the anode. Now, at the anode is platinum, the cathode is platinum, made of platinum, same as the anode. Now, platinum are inert electrode. We still come to that. Platinum is an inert electrode, meaning that it doesn't influence the ion that will be discharged during electrolysis, but we'll come to that later. And so here now, at the cathode, what happens? Because only hydrogen is present at the cathode, obviously, hydrogen will be discharged. It's not competing with any other ion. So we have it like this. Hydrogen ion. Since it's 2 hydrogen ion, it accepts 2 electrons and then being discharged as hydrogen gas. Now this process is known as reduction. Take note. I didn't say that in our previous example, but why? Because it is gain of electron. Now let's get to the cathode now, the anode, sorry. Now we have 2 competing ions at the anode, which is SO4 2- tetraoxobasis ion and hydroxide ion. Both migrate to the anode. But obviously, by effect of position, as you look at the anions now, starting from the fluorine, SO42 minus, and then NO3 minus, chlorine, bromine, hydrogen, and OH. You see that SO42 minus and OH. OH is below in the activity series. And because of that, OH is discharged. So we have it as this 4OH to give 2 molecules of water plus oxygen gas plus 4 electrons. Now, this is electron loss and it is oxidation. And so that's about the electrolysis of water. And we can see that the gas liberated at the anode is oxygen. Oxygen is collected over the acidified water here, and hydrogen is collected above the cathode here. So that's about the electrolysis of acidified water. Another example here is electrolysis of copper 2 tetraoxosulfasis, aqueous copper 2 tetraoxosulfasis, using copper or platinum as cathode and using graphite as anode. Well, the electrolyte ionizes as shown. Copper 2 tetraoxosulfasis ionizes as copper 2 ion and SO42 minus ion. And water ionizes partially as hydrogen ion and hydroxide ion. Well, the positive ions move to the cathode and the negative ions move to the anode. Well, at the cathode now, copper and hydrogen migrate, but copper is discharged because it is a lower ion in the activity series. So hydrogen migrates to the cathode, where copper ion is discharged because of its lower position in the activity series. Hence, we write like this: copper at the anode accepts 2 electrons and be discharged as copper. So you notice that at the cathode, there will be a deposit of copper on the cathode because copper is discharged. And this process is known as reduction. What then happens to the hydrogen ion? It goes back into the solution. And then, now at the anode, again, very clear, obviously, OH should be discharged because it's lower in the activity series. So, both SO42 minus and OH migrates to the anode, where OH is discharged because of its lower position in the series. And so we have becoming 2 molecules of water plus oxygen plus 4 electrons, and this is known as oxidation. The question is, what then happens to the SO4? It goes back into the solution, and that's why another question you can be asked in JAMB or WAEC about this electrolysis of copper 2 tetraoxosulfasis is that during the electrolysis of copper 2 tetraoxosulfasis, dilute or aqueous copper 2 tetraoxosulfasis, what happens? Hydrogen hydrogen is discharged at the cathode, and that is wrong. B, SO42 minus is discharged at the anode. That is wrong. C, the electrolyte becomes more acidic. And D, none of the above. The answer is C. And that's because hydrogen returns back to the electrolyte. And then SO4 returns back to the electrolyte, while only copper and OH is discharged. So at the end of the day, hydrogen ion and SO42 minus are gathering at the electrolyte, and the two combine to give you acid, H2SO4 acid. And because of that, the electrolyte over time becomes more acidic. So that's that about that. So another factor that influences the discharge of ion during electrolysis is concentration of ions. You see, an increase in the concentration of ion promotes the tendency of that ion to be discharged, even when it is not the lower ion in the activity series. But understand that the influence of concentration of an ion is only effective when the two competing ions are close in the activity series. I will explain what this means now. You see, let's illustrate the effect of concentration of ion using electrolysis of concentrated sodium chloride. You know, the electrolyte ionized this way: NaCl, Na plus Cl minus. Please, during concentration of electrolysis of any concentrated electrolyte, you must note concentration. You must add this to it. Concentration I. And for water that ionizes reversibly, H plus and OH minus, you put low. I add this only when I'm doing concentrated electrolyte. Now this migrates to the cathode, and this to the anode. Now, if you watch closely, sodium and hydrogen migrates to the cathode, and the concentration of sodium is very high, but concentration will not make sodium to be discharged. That's because concentration has become ineffective here. Why? Because sodium and ion and hydrogen ion are far apart in the activity series. You know, we have potassium, sodium, magnesium, potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, before hydrogen. So they are far apart. So the concentration of sodium does nothing here. So hydrogen is discharged. Let's put that into statement. At the cathode, sodium and hydrogen migrate to the cathode, but hydrogen ion is discharged because it is the lower ion in the series. The effect or the influence of concentration of sodium ion is ineffective because sodium and hydrogen ion are far apart in the activity series. And so what the statement means that the influence of concentration is only effective when the two competing ions are close in the activity series. So they are not close actually. So we are going to have hydrogen plus 2 electrons because it must be a gas. And this is known as what? Reduction. So reduction often occurs at the cathode. Now let's take at the anode now. At the anode, chlorine and OH migrates to the anode. Now, chlorine has high concentration and is discharged actually. Now, OH is not discharged even though it is the lower ion in the activity series. But that's because chlorine and OH are relatively close in the activity series. You know, we have fluorine, SO42 minus, NO3 minus, then chlorine, bromine, iodine, and OH. So OH and chlorine are relatively close, just 2 ions apart. And because of that, OH is not discharged. So the influence of concentration of chlorine here is effective. Migrates to the anode where chlorine is discharged because of its high concentration and it is close to OH in the activity series. So we're going to have Cl minus, because it must be a gas, so 2Cl, to give chlorine gas and liberate 2 electrons, and this is known as oxidation. So that's that about that. Now, let me give a quick classwork. Explain the electrolysis of concentrated lead 2-trinitrate 5. I'm not going to solve this, but pause and guess what should be discharged at the cathode and the anode. Okay? Well, at the cathode, obviously, because this is concentrated, concentrated means it contains little amount of water. And because of that, lead is going to look like this. The electricity of copper is going to look like this. The ionization of copper is going to look like this. PbNO3, Pb2 plus NO3 minus 2 of this, and then water, hydrogen ion plus OH minus. Now concentration, this is high and this is low. Well, between lead and hydrogen, by effect of position, hydrogen should be discharged. But because of the concentration of lead is high, and if you check the activity series, lead and hydrogen are close to one another, so lead is discharged due to its concentration and being close to hydrogen in the activity series. So you see that this activity series, you have to memorize the order so you can tell. And then between NO3 and OH, OH should be discharged no matter the concentration of NO3, because it is far apart from OH in the activity series. Then OH should be discharged at the anode. So at the cathode, lead is discharged, and at the anode, OH is discharged based on its position. The concentration of NO3 is ineffective here.